Hello, sir. I am Ashutosh Kharde with my colleagues Sushant, Saurabh, and Ganesh, presenting you on topic frequency response analysis of any structure or bridge, and finding mode shape and max deformation and stresses for the bridge. So next slide. Introduction. So there are many bridges which are constructed in the world, but as the humans are evolving and the world is evolving, humans are finding ways and the less time consuming means to communicate. So the bridges constructed should be able to withstand the large force which are being exerted by any car or people who bypass through that bridge. So to make it secure and to know the amount of load it can bear at the most uh, so the amount of load which it can bear the most, which is the important factor for construction of bridge. So to measure and to demonstrate uh, the bridge analysis, we'll be doing a simple analysis of bridge, and through that we'll be finding the max deformation of that bridge and also the different modes and stresses for that. So next slide. Here are some steps we'll be following upcoming slides. So first is we'll be making the CAD model, which is made in SolidWorks, and the file which is been inserted then in ANSYS in the second step, and after that we'll be applying the boundary conditions for the bridge, and after that we'll be meshing that bridge, uh, and then at, at at last we'll be applying forces on that bridge, and at last we'll be finding the solutions as deformation and equivalence stresses for the same. Next slide. Yeah.
So basically, for the construction analysis of that bridge, what we have done is we have constructed a bridge in SolidWorks, and it was simulated for frequency responses analysis with total deformation, mode shape, and equivalent one mass stresses. So the material which we have used during this is structural steel. The dimensions is 1700 mm into 500 mm. The height of the bridge is 700 mm. The type of bridge which we have used is Warren Truss bridge. Next slide, please. So this is the CAD file. So basically, we have designed the bridge in the CAD file. We have in the SolidWorks we have designed it. We have designed it by extruding the material and adding adding the material. Next slide. So meshing is one of the key components to obtain accurate results from an FEA model. The elements in mesh must take many aspects into account to be able to decretize stress gradient gradually. Typically, the smaller the mesh size, the more accurate solution, as designs are better simply across the physical domains. The trade-off is that for the higher accuracies, the larger simulations is needed, and it takes lots of amount of time. Next slide.
So myself is Sushant, and I'll be explaining about the meshing part here. So we took a meshing size of around 20 mm, and the method we used was automatic method, which will let the software decide which method is appropriate for meshing. And the conditions we applied, like we use the force for stress analysis, like von Mises stresses. So we applied a perpendicular force of 3000 Newton on the bridge. So we found a deformation. We found some equivalent stress over here. So in the next slide, these are the obtained graphs we took out from the results. So we found different frequency responses, like the method used was Lang's iteration. So at different modes from 1 to 6, we can see there are different frequencies we obtained. and the deformation at every other frequency is slightly different than the other. So at mode 1 we found 6.72, mode 2 we found 6.73, and at the highest deformation was 8 and 10. So that was at 182.05 hertz of frequency. So in the graph here, we can see the orange one is the frequency hertz, and the gray band represents the deformation in over different frequencies, and these are the number of modes. The same, this table is shown in the tabular form. So in this we found the equivalent von Mises stress of 500 nodes. It cannot actually be found around infinite number of nodes, but we took it a constant force of 500 for 500 nodes. So Ganesh, please go ahead.
These are the one Mises stress obtained at different mesh size. For 15 mesh, we got 10.25, and for 20 we get it 11.01. Next slide. These are the deformations at the different frequencies, where for in a first, for a frequency of 78 hertz, we get deformation of 6.724, and for 128 hertz, we get 6.751. Next. Here is the other, where for 180 hertz, we get 8.543 deformation, and for 182 hertz, we get 10.19 deformation. Next. So the result and conclusion is the analysis of bridge of a structure still had a maximum deformation of 10.404 and 11.03 megapascal of maximum equivalent stress. According to the analysis, the bridge base remains upright even at 182 hertz. However, the bridge distorted when a 3 kilonewton perpendicular force was applied to it. Next slide. Thank you.